Hi, my name is Siri Mathisen, and I'm a researcher at Sintef Energy Research.
And I'm Kristine Lund Bjørnås, a researcher at NINA.
And today we will tell you about sustainable flexibility metrics and how we have worked together with a framework to measure economic flexibility and hydropower relative to environmental sustainability. So the power consumed and the power production must always be balanced. And this would be tricky enough if the production should equal a constant demand, but the demand is also time varying and elastic with respect to price. Besides, the high share of power production from variable renewable energy sources demands access to flexible resources that can continuously balance electricity production and consumption. This can be provided by regulated hydropower. And in this context, regulated means that the energy in the shape of water can be stored in a reservoir and that the discharge through the power plant can be varied. And that means that the power can be altered depending on the demand. The expected demand is communicated through a price signal as a result of a market clearing. Flexibility can be exploited to save water for periods with high prices, usually reflecting a high demand.
Yes, so this does not come without its backsides. And one of the biggest challenges for flexible hydropower is to operate within environmentally sustainable boundaries. As river and lake ecosystems are already under massive pressure from a whole host of stressors, and freshwater biodiversity is in rapid decline, with the flow modification being one of the major threats to biodiversity, as flow is the master variable shaping ecosystem processes and functions. And organisms are adapted to the natural flow regime of their home river. And this flow regime can be divided into the elements timing, magnitude, frequency, duration, rate of change. So storage hydropower gives rise to a new and regulated flow regime where these 5 aspects are manipulated to some extent. So it makes sense to use the flow regime and these elements as links between environment and production, as is done, for instance, in Norway, where the 2 most common environmental constraints are the minimum flow requirements and the down ramping restrictions for hydropeaking operations.
So therefore, hydropower operation is subject to operating terms, which are enforced in the concessions of the hydropower plants. So they are licensed to operate. And these operating terms should reflect the need for environmentally sustainable use of water, and they can include environmental constraints like the ones mentioned by Kristine. However, the environmentally friendly way of operating the hydropower system can be in conflict with the need for flexible power production. And these trade-offs between the need for flexibility and the need for the environment can be difficult to evaluate. And therefore, we need a generalizable decision support framework that includes both environmental concerns and flexibility. This framework could assess the impacts of updated environmental regulations on the potential loss of energy and flexibility and what this means for the environment. To measure the economic flexibility of a hydropower system, we have used 2 metrics in this work: the flexibility factor, or the value factor, and the equivalent electricity storage. So the flexibility factor, or FF for short, is the relationship between the achieved price of a period and the average price. And now please click once, Kristine. There you go. So the achieved price, that is here pi with an asterisk, that's the average income divided by the average production. So if we produce a lot when the price is high, we get a higher income than we would get for the same production when the price is low. So therefore, being able to produce when the price is high will lead to a high flexibility factor. The equivalent electricity storage is a representation of the flexibility that is lost due to a change in the operating conditions of the hydropower system. For instance, when an environmental constraint is introduced. So basically, we can say that for the constraint system, we can add a battery that provides us with the same flexibility that we lost in the system due to the introduction of the constraints. And this battery or this equivalent storage, it's parameterized with a storage size in gigawatt hours, like how much energy should you be able to store, and a charging and discharging capacity in megawatts to be able to compensate for the flexibility that is lost. And then we have a third parameter of the equivalent electricity storage, which will be the net yearly flexibility income. Please click once again, Kristine. There you go. And this is the income that is lost from the system due to the change in operating conditions, but it's not a whole loss, it's just a flexibility loss. So we want to subtract the average loss of income. So we are not interested in measuring all the production that is lost because we have less water available, for instance. What we want to measure here is the income that is lost due to us not being able to move production in time. And that is a loss of flexibility income. Next slide, please. So then we have some metrics measuring the loss of flexibility, but how do we calculate this? So I suppose all power producers, they could simply use production data. But for this research, we used a simulation tool with an optimal production planning strategy. And this is the PRODRISC model. And as input, we provide a hydropower description with reservoir size, production curve, and topology, describing which reservoir will receive the output from which plant, and like where the water flows. And then we need price and inflow scenarios to provide a strategy that is robust towards many possible weather and price years. And finally, we must describe the operating terms of the system, for instance, the environmental constraints. And what we get out of this model, that will be simulated production, income, and reservoir curves that we then can use to calculate our flexibility metrics. Next slide, please.
Yes, and for this project, we had to choose environmental metrics, and we did a little search in the literature to find that there is really no shortage of already available environmental metrics to quantify the environmental effect of hydropower. For instance, this review found well over 3,000 different metrics, including pure measurements, statistics, and indicators concerning the majority concerning the operating phase of hydropower. And in Norway, environmental metrics can, for instance, be found in these two frameworks that were developed in earlier generations of this research center: the environmental design framework and the classification system for hydropeaking impacts. So we decided to use metrics from these already existing frameworks for the SysFlex project. And so I can't go into detail because of time, but for the environmental design, information about habitat characteristics in the river and hydrological bottlenecks can be used together with expected response in fish populations, often salmon, to estimate the metric in yellow here, the smolt production potential. Whereas within the classification system or hydropeaking, there are two axes of evaluation: the hydromorphological effect factors and the population viability factors, also fish population. And these factors are all scored from very small effects to very large effects based on predefined criteria, and then combined into a total classification score. But in our case, we only had data to use the hydromorphological effect factors. So to summarize, we ended up with these 5 metrics in the method. The 3 concerning the economic flexibility that Siri talked about, and these 2 latter environmental metrics. So to compare these, they were scaled for each case study application to highlight and compare differences between scenarios in a multivariate illustration that you will see soon. And the case systems that we landed on was the Aura and the Suna River. They're both located in mid-Norway, and they have both just been through our relicensing process. So we set up 4 contrasting scenarios, the model, using different environmental constraints, more or less corresponding to the historical constraints before relicensing and the new constraints after relicensing, and even stricter terms that were suggested during the relicensing process, and even more drastic environmental constraints to highlight the whole spectrum of low priority to the environment to very high priority to the environment.
So for all of these cases, we measured flexibility and environmental sustainability. We then scaled the results to be able to show relative change between the cases, and we were therefore able to plot the metrics next to each other and show the consequences on the economic flexibility and the environmental conditions due to the change of operating terms. For instance, for Aura, we see that progressing from case A3 to A4 will give a significant rise of smolt production, but also a decline in power production. On the other hand, we see that the flexibility factor is slightly higher for case A4 than for A3. The flexibility factor we see on top here. And we see that for all of the cases, the flexibility factors, they are really similar to each other. So case A3 has a loss in production due to the introduced constraints, but a higher flexibility income on the to the left than the unconstrained case. For Suna, on the other hand, we see little loss in power production, but we see a significant loss in flexibility income between the unconstrained case S1 and case S2. And there is no difference between cases S2 and S3 when it comes to flexibility income, nor combined hydromorphological effect, but S2 has fewer environmental constraints than case S3, which has more environmental constraints. Yes, so S2 with fewer environmental constraints has higher power production than case S3. So these considerations are really easy to make when we see the results presented like this. However, it's important to choose the scales of the metrics sensibly. Otherwise, it will just be a picture, but a nice picture. So to conclude, the work presented here makes different assumptions and their influence on the environment and the economic flexibility visible. And it also helps make the choice between economic flexibility and environmental sustainability more informed. So this could be a decision support tool in licensing processes for both NVE and for the companies preparing to apply for a license when assessing the trade-offs between flexibility and the environment.
And for considering the environmental sustainability and environmental metrics, we barely scratched the surface during this SysFlexMet project, but we are continuing now in RenewHydro and in work package 2.1. And there is definitely more work needed to test and validate and further build upon preferably existing metrics rather than continuously reinventing the wheel. And there is also a third dimension of sustainability, the social sustainability, that could be included into this decision support framework in more extended assessments in the future.
Thank you.
Thank you.